Welcome back, everyone. In this video, I'll be continuing the lecture for the trig derivative section. So number 4 here, we want to find the derivative y prime if y equals 2x over 6 minus tangent of x. Now, we clearly see, hopefully at this point, what we want to do first is we want to set up the quotient rule because we have division. So y prime, we're going to do the quotient rule. We are going to have the derivative of the top, the derivative of 2x, times the bottom, 6 minus tangent of x, and then minus the top, 2x, times the derivative of the bottom, 6 minus tangent of x, all over the bottom squared, 6 minus tangent of x, all squared. All right, so how do you want to do this? Well, pretty much with the quotient rule, we don't care if there's trig functions, exponential functions, power functions, just numbers. We set it up and then we go to work. We see these two derivatives here, and this is what we want to take care of. And the derivative of 2x is just 2. And then it's multiplying 6 minus tangent of x. Then we have minus 2x. And the derivative of 6 is 0. And the derivative of tangent of x is secant squared of x. Because of the minus sign, this is going to be minus secant squared of x. And then we know for the bottom, we're just not going to touch it until the very end. When we feel like we're simplified, can we use it to cancel anything or not? Okay, so we're right there. Now, what would you want to do next? Let's kind of look at this. Well, sort of a involuntary thing, or the thing you should think about automatically, is when you have multiplications or distributions, you should just do them right away. Realize I just forgot to include a parentheses here to close the bigger one off. But that should be the natural thing. Now, it's not necessarily going to be always the thing you want to do, because if you have something in common with each one, you can factor it out. Ultimately, if you look at what's in common with these two things, only 2 is in common, and that's not going to help us much. So let's go ahead and just distribute everything through. Take the 2 through, we get 12 minus 2 times tangent of x. And then when we multiply the negative 2x times negative secant squared of x, we get a plus 2x secant squared of x. Once again, over our denominator, which we're not touching, 6 minus tan x squared. And then I want to ask myself, should I try to simplify? Can I simplify anymore? Well, what I would notice here, why I would say I'm done, I'm stopping. The only thing I could think to do is to factor out a 2, because we have a 12, a 2, and a 2, which we could factor out. But usually if you're factoring out just a number, I personally only like to do that if it's going to help me cancel something on the bottom. Otherwise, it's just a number. Unless if that number is something really messy, like e times pi plus the square root of 3. You know, something really messy. If it's just 2, I leave it there. The other reason why I know I don't want to try to simplify anymore, because it probably won't, is the tangent of x here does not have an x with it. The secant squared of x here does have an x in front with it. And that means even if we can figure out some really nice trig identities to try to use, and you can use a Pythagorean identity on secant squared of x to get a tan squared of x, it's still not going to help because this x here is going to throw off everything. So really, I would say, yes, I'm done. Now, what I want to go ahead and do before I move on to the next problem is really show you how you can check your derivatives using Wolfram alpha. I already have it typed in, so I don't spend time typing it in. But if you want to do derivatives in Wolfram alpha, it's just like limits. You just, instead of doing the limit of, you say derivative of, and then, you know, we're not plugging in a number here, so I don't plug in anything afterwards. Now I'll show you how to do that if you want to right after I explain this. But what I want to point out is the way I wrote this. Whenever I do the derivative of, I always have, and it highlights for me, which is really nice, this first parentheses and last parentheses, I just put the entire function in there. And if I have a fraction, which I do, I put the entire top in its own fraction. So the 2x is in its own fraction, or in its own parentheses, not fraction. My apologies. And then the denominator, the 6 minus tangent of x, is also in its own parentheses. And that way I can see it's going to read it correctly. Now, it's nice that it spits out the same answer, but you want to make sure you're learning and going through the steps to get it. The only thing it does is at the end, they have the 2 factored out. And that's the only difference if you compare their answer to our answer. And it can really help you feel confident in the fact that you not only did it correctly, but you simplified it as far as you really can. Because if there's something that's going to make it simplify a lot further, Wolfram Alpha will figure it out. And if it looks totally different from yours, either you have a wrong step or they simplified it further. But looking at this, I would say we're good to go. Now, if you actually wanted to do the derivative at a point and check, you could write down your derivative formula in here and then plug it in, or you can just write derivative of whatever and then at whatever x value. So let's say we wanted to do this at x equals, I don't know, pi. Well, I could type it in like this, hit enter. It's not going to show me the derivative formula specifically. It's going to show me the result if you take this and plug in pi. Now, I don't actually want to do it here, so I'm not going to plug in pi and make sure it's 6 plus pi over 18. But apparently, if you plug in pi, that's what you should see. Okay, but I just wanted to stress that when you plug in number for a derivative, just like we've been doing it by hand, you got to figure out the formula first, which is what this does, and then you plug it in. You can't just plug in pi for x and then write derivative of, because it's going to give you 0, because it would just be doing the derivative of a number. Okay. All right, so with that, I wanted to actually work on one problem that was an application. It's pretty nice in that trig functions have a lot of applications. However, the way typically in a trig class you use the applications, it's for periodic functions, meaning things that go up and down over time, or you can very clearly see it go around in a circle. Well, the nice thing, and one of the important things about studying physics, is that it uses trig functions to model springs vibrating. And I wanted to go ahead and draw this picture for you. This will be a picture that you're given if you need it. But I want to go ahead and draw it as we work through the problem. So it says a mass on a spring vibrates horizontally. What this is actually going to tell me is that I have, this isn't an XY plane necessarily, this is just a wall. The spring is attached to a wall. And to kind of draw this spring, think about it like this. Think about a slinky, if that helps. And then you have a little mass at the end. I'll fill that in. Right, and it vibrates left and right. Now, maybe it helps to, it looks sort of like it's floating, but just pretend it just goes left to right here. So it can move to the right, it can move to the left. Okay, and the motion of the mass is modeled by x of t equals 4 cosine of t. So you could imagine if you took this spring and you grabbed the mass and you pulled it out, what would happen? Is it's going to come back and then it's going to go out and it's just going to keep going back and forth. So that's why the cosine of t pops up there. But we're mostly interested in the formula. So I'm going to go ahead and actually write down the formula. X of t equals 4 cosine of t. Right, where it goes back and forth. And the point where it sits naturally, you don't really need to know this, but it's called the equilibrium point. So if you ever have a spring or a slinky and you kind of spread it out, it might keep its shape at some point. If you make it too compressed or too wide, then it's going to go back and forth until it finds its equilibrium. Okay, so we have this formula. Ultimately, this is what we're most interested in. T is in seconds and x is in inches, so we'll just keep track of that. We want to find the velocity. What does that mean? We want to do the derivative, then use this to find the velocity at time 2 pi over 3. And then the last question related to that is, which way is the mass moving? So is it going to be moving left or right at time 3? We'll be able to interpret that after we get the velocity and everything. All right, so velocity v of t, the velocity is just the derivative of our function, x prime of t. And what's the derivative of 4 cosine of t? Well, this one is pretty straightforward. The number 4, we know it's going to stick around, and then derivative of cosine of t is negative sine of t. So that's all we have. And because we're going to be using this equation, let's just simplify it. This would be negative 4 sine of t. All right, so that's our velocity. What do we want to do is we want the velocity at time 2 pi over 3. And if you want to type that in your calculator just to get a gauge of how long that is, it's roughly 2. So it's pretty much asking what is the spring doing? What is the mass doing? How is it moving after around 2 seconds? V of 2 pi over 3, we take our velocity formula, -4 sine of t, and we plug in t, 2 pi over 3. Now, what is sine of 2 pi over 3? Maybe you have to use a calculator, but this is on the unit circle, and you should know some way how to figure this out. It's in quadrant 2, so sine is positive, and the reference angle is pi over 3. That's when sine is the square root of 3 over 2. So this would be the square root of 3 over 2 times -4. Now you can simplify this a little bit because the -4 and the 2 cancel out, and you get -2 square root of 3. This is the velocity. Now this is in inches per second. And so where distance was inches and time was seconds, if you wanted to write the units. But the other question, now that we got the velocity, is which way is it moving? Is it moving left or right? Well, the velocity is negative. So think about x is our kind of our x value. As it gets bigger, it goes up. It's going to move to the right. So the right, if we're moving to the right, x is getting bigger. Or a better way to say it is x is increasing. So what would that mean if we're moving to the right? If x is bigger, if it's increasing, that means the velocity is positive, greater than 0. Now, if it's moving to the left, the opposite happens, right? Correct? Because if we move to the left, let me use a different color just to write this. If it's moving to the left, what's happening is x is getting smaller. And if x is getting smaller, it's decreasing. If something's decreasing, its derivative, which is its velocity in this case, is negative. Okay, so if our velocity is negative, it's moving to the left. If our velocity is positive, it's moving to the right. And this is a negative number. You can type it in, but it's just -2 times a positive number is negative. So it's going to be moving to the left. If the velocity was positive, it would be moving to the right. If the velocity was 0, what that would tell you is that you're either at one end or the other. It's compressed completely. It stops for a brief second, or it's fully extended out. It stops for a brief second. So you wouldn't really be moving if the velocity was 0. All right, but once again, it's nice to just throw in these applications every once in a while to know that we're not just doing derivatives for no reason. There's a reason we like to do them, and they pop up all the time, especially in physical things. So I will see you. Actually, let me not say I'll see you in the next lecture, because I wanted to go ahead and make sure that I summarize the derivative rules so far, like I've been doing in these sections. And then also I want to bring up really what we did in this section and show you a little pointer, how you can help memorize just a little bit. All right, but what old things do we know? Well, before this section, we knew how to do the derivative. These are our derivative rules. So everything I'm going to write here is saying we can do the derivative of e to the x. We could do the derivative of x to the n. We could do the derivative of just x. We know that's 1. We could do the derivative of just a number. We know that was 0. And also in the previous sections, we learned how to do derivatives with addition, subtraction, multiplication, and division. And we've used all these throughout this section as well. The new stuff, kind of adding to our arsenal, is the derivative of the 6 trig functions. And I wanted to make a little table here, not just so you could have a table, but also to point out something. Notice that 3 of the derivatives, this is its function, this is its corresponding derivative on the right, 3 of the derivatives have negative signs, and then the other 3 do not. Which ones have negative signs? Well, it's the ones that original function starts with c, all of the cos. So if you're doing the derivative of a co-function, cosine, cotangent, cosecant, the ones that start with c's, then its derivative is going to be a negative, going to get a negative sign. So that's pretty much the only way you can help memorize these is the derivative of the C starting functions for just trig functions. Of course, if there's other types of functions that start with the letter C, this has nothing to do with it. But for trig functions, if your function starts with the letter C, then there is a negative sign. And then the other three, sine, tangent, and secant, don't start with C, and they don't have negative signs in their formulas. Okay, so I talked a little bit about how you can sort of help yourself remember the derivatives themselves. Sine really goes with cosine. Derivative of sine involves cosine. Derivative of cosine involves sine. Tangent goes with secant. Derivative of tangent is secant squared. And then the derivative of secant is secant times tangent. And then also cotangent goes with cosecant. The derivative of cotangent has a cosecant squared in it. Derivative of cosecant has cosecant and cotangent in it. Pretty much it's up to you how you memorize them. I just found when I was a student, the hardest thing for me to remember was which ones get negatives. And then someone just pointed out to me one day that it's all the C's. And I thought, wow, that would have been great to hear when I first learned about them. So I want to make sure I threw that in there for you. But I'll see you in the next lecture.